Imagine a robotic arm reaching out to grasp an object. How many ways can it move? This is where degrees of freedom, or DOF, come into play. In simple terms, DOF refers to the number of independent movements a robot or any mechanical system can make. Each joint on the robot represents a degree of freedom. Think of your own arm. Your shoulder allows for movement in multiple directions. Your elbow bends and straightens. Your wrist rotates and flexes. Each of these joints contributes to the overall dexterity of your arm. Robots, like our arms, rely on DOF to navigate and manipulate their surroundings. A higher number of DOF generally translates to a wider range of motion and greater flexibility. This is crucial for robots designed to perform complex tasks, especially in dynamic and unpredictable environments. Now, let's delve deeper into how DOF directly impacts a robot's range of motion. Imagine a simple robotic arm with only 2 degrees of freedom. This arm might be able to move up and down and perhaps rotate at its base. While this limited mobility might suffice for simple tasks, such as moving objects along a single axis, it would be insufficient for more intricate maneuvers. In contrast, consider a robotic arm with 6 degrees of freedom. This arm can move up and down, rotate at its base, extend and retract, and even rotate its wrist. This increased freedom of movement allows for a much wider range of motion, enabling the robot to access and manipulate objects in a 3-dimensional space with greater ease and precision. The number of DOF determines the robot's workspace, or the volume within which it can operate. A higher DOF robot has a larger and more complex workspace, expanding its potential applications. To illustrate this concept further, let's compare 2 robotic arms. A 2 DOF robotic arm commonly found in basic pick-and-place applications, and a 6 DOF industrial robot arm used in manufacturing. The 2 DOF arm, with its limited movement, excels at repetitive tasks along a fixed path. On the other hand, the 6 DOF arm, with its enhanced flexibility, can perform more intricate operations, such as welding, painting, and assembly. The additional degrees of freedom allow it to approach objects from different angles, making it suitable for tasks that require greater dexterity and precision. Section 4. The power of more enhanced flexibility and precision. The advantages of increased degrees of freedom extend beyond just a wider range of motion. A higher number of degrees of freedom also translates to greater flexibility and precision in movement. Robots with more degrees of freedom can maneuver through complex environments with greater ease, avoiding obstacles and reaching targets that would be inaccessible to their less articulated counterparts. This enhanced flexibility is particularly crucial in fields like robotic surgery, where robots must navigate the intricate and delicate structures of the human body. The precision afforded by a high degrees of freedom surgical robot allows for minimally invasive procedures, reducing trauma to the patient and improving surgical outcomes. Section 5. Degrees of freedom in action, real-world applications. The impact of degrees of freedom on robotic capabilities is evident in a wide range of real-world applications. In manufacturing, robots with multiple degrees of freedom are employed for tasks such as welding, painting, and assembly. Their precision and repeatability make them ideal for these tasks, improving efficiency and product quality. In healthcare, surgical robots with high degrees of freedom are transforming the operating room, allowing surgeons to perform complex procedures with greater accuracy and control. Humanoid robots, designed to mimic human movements, rely on a high number of degrees of freedom to walk, grasp objects, and interact with their surroundings in a human-like manner. As technology advances, we can expect to see even more innovative applications of degrees of freedom in robotics, pushing the boundaries of what's possible in automation and human-robot collaboration.